12 hours. That's the theoretical reserve of breathable emergency air a nuclear submarine is required to carry, because in theory, it should never need to use it. We're used to imagining a submarine as a giant scuba tank, carrying around enough air to last a voyage. But the truth is far stranger than that. A modern nuclear submarine doesn't store the air its crew breathes. It manufactures that air, second by second, hundreds of meters beneath the surface, in the middle of the open ocean. So what happens if that system fails? How much real time does a crew actually have before the air they're breathing turns against them? Today we're going inside the invisible system that keeps 150 people alive underwater for months at a time, without ever touching the surface. And by the end, you'll understand why the real danger was never running out of oxygen. It's something far quieter and far more dangerous. Let's start by dismantling the most common assumption people have. Most people picture massive compressed air tanks, like scuba gear scaled up to the size of a warship. But in reality, a nuclear attack submarine can stay submerged for weeks, sometimes months at a stretch, and no tank on Earth could hold that much air. The real solution is far more radical. The submarine generates its own oxygen directly from seawater. The process is called electrolysis. An electrical current, powered by the nuclear reactor, splits water molecules into hydrogen and oxygen. The oxygen is released into the submarine's internal atmosphere. The hydrogen, dangerous and highly flammable, is vented overboard through a carefully controlled exhaust system. Imagine that machine running non-stop, 24 hours a day, manufacturing the very air you breathe out of the ocean surrounding you. As long as the reactor has fuel, and that can last for years, the submarine can produce oxygen indefinitely. In theory, the only real reason a nuclear submarine ever has to return to port is food for the crew, not air. Before nuclear power made this possible, things were very different and far more dangerous. Older diesel-electric submarines from the mid-20th century had no way to generate oxygen indefinitely. They relied on compressed air tanks and, crucially, had to surface regularly to run diesel engines and refresh their atmosphere. Crews on those boats lived with a hard, ticking countdown. Every hour submerged was an hour closer to genuinely running out of breathable air, with no backup beyond returning to the surface. The shift to nuclear propulsion didn't just change how submarines moved. It completely rewrote the rules of how long a crew could survive underwater, turning what used to be a fixed countdown into something theoretically unlimited. But here's the twist almost nobody knows about. Producing oxygen is only half the problem. The other half, the far more dangerous half, is getting rid of carbon dioxide. Have you ever thought about how much CO2 a single person exhales inside a sealed space? Now multiply that by 150 crew members, locked inside a steel tube, for weeks at a time. Without a system to strip that gas out continuously, the air would turn toxic long before oxygen ever ran low. This is where the submarine's true silent hero comes in, the CO2 scrubbing system. It uses a chemical compound, typically lithium hydroxide or liquid amine solutions, that physically captures carbon dioxide molecules from the recirculated air and binds them chemically. Air is pulled through these filters again and again, in a constant cycle, before being pushed back out through the boat. If this system fails, oxygen levels can remain perfectly normal, while the air itself slowly transforms into an invisible poison. And this is exactly the danger most people get wrong. We fear running out of oxygen, but the real silent killer is excess CO2. At low concentrations, it causes headaches and fatigue. At higher levels, mental confusion, dizziness, loss of coordination. At extreme concentrations, it can cause loss of consciousness within minutes, even while oxygen levels in the same air remain completely normal. Picture being fully awake, breathing normally, feeling nothing physically wrong, while your mind slowly clouds over and you have no idea why. That's why submarines constantly monitor CO2, oxygen, and even trace toxic gases produced by onboard machinery, like carbon monoxide. Sensors distributed throughout the hull analyze the air in real time, around the clock, because a change too gradual for the human body to notice can quietly become a death sentence if nobody catches it in time. This monitoring isn't a passive background task either. It shapes daily life on board. Designated crew members check atmospheric readings multiple times per shift, logging oxygen percentage, CO2 levels, and humidity by hand even when automated systems are running normally. It's treated with the same seriousness as monitoring the reactor itself. Drills are run regularly, simulating a scrubber failure or a sudden spike in CO2, so that every crew member, not just the specialists, knows exactly what to do in the first 60 seconds of an emergency. Have you ever wondered what it's like to live somewhere where checking the invisible air around you is as routine as checking the time? For a submariner, that's simply Tuesday. But technology, no matter how advanced, depends on maintenance, power, and components that can fail. So what actually happens when something goes wrong, hundreds of meters below the surface? In August 2000, the Russian submarine Kursk suffered a catastrophic explosion during a naval exercise in the Barents Sea. While the initial disaster was triggered by a faulty torpedo, what happened in the hours that followed exposed exactly how fragile life support systems can be under pressure. A group of sailors survived the initial explosion, taking shelter in one of the rearmost compartments of the sunken submarine. For hours, possibly longer, they fought against rising CO2 levels and dwindling oxygen in an increasingly small pocket of air, while rescue efforts were slowed by depth, weather, and international miscommunication. The world watched, holding its breath, as time itself became the cruelest enemy of all. The Kursk became a brutal reminder that no matter how advanced the technology, the margin between life and death underwater can be measured in hours, not days. The Kursk wasn't the only time the world came close to this kind of disaster. In 2005, a Russian deep-sea rescue submersible became entangled in fishing nets and cables off the coast of Kamchatka, trapping 7 crew members nearly 200 meters below the surface with a dwindling air supply. Unlike the Kursk, this story had a different ending. An international rescue effort, including a remotely operated vehicle rushed in from the United Kingdom, managed to cut the vessel free just hours before its emergency air reserves would have run out. The crew survived, but the incident sent the same chilling message around the world's navies. Even with redundant systems and trained crews, the line between a routine mission and a race against a depleting atmosphere can collapse in an instant. It reinforced something military planners already suspected, that rescue capability matters just as much as the life support systems themselves, because no amount of air management solves the problem of a boat that physically cannot move. The Kursk wasn't an isolated case either. Throughout submarine history, smaller, less publicized incidents have repeatedly shown how quickly an atmosphere can turn dangerous. Equipment failures, electrical fires, and flooding have all, at different points, knocked out scrubbing systems or oxygen generators for critical stretches of time. In several documented cases, crews have had to rely entirely on manual backup procedures, hand-cranking emergency systems, or distributing individual chemical oxygen candles, devices that burn a solid chemical compound to release breathable oxygen as a last resort. These candles aren't meant for long-term survival. They're meant to buy time, sometimes just minutes, for a crew to reach safety or get a failed system running again. Every one of these incidents quietly reinforced the same lesson the Kursk taught the world in the most public way possible. Air management isn't a background system on a submarine. It's the single most fragile thread keeping everyone alive. There's also a psychological dimension to all of this that rarely gets discussed. Submarine crews don't just deal with the physical risk of bad air, they live with the constant awareness of it. Veterans of long deployments describe a particular kind of tension that builds over months underwater, knowing that the very air around them is artificial, generated, filtered, and constantly at risk of subtle failure. Some describe headaches that crews simply learn to live with during long patrols, a sign that CO2 levels, while still within official safety limits, sit higher than what the body is used to on the surface. Submariners adapt. Their bodies adjust to slightly elevated baseline CO2 levels the same way mountain climbers adjust to thin air, except in reverse. It's not something talked about openly, but it's part of what makes submarine duty among the most physically demanding postings in any navy. After tragedies like the Kursk, navies around the world dramatically overhauled their safety protocols. Today's submarines are built with redundant systems stacked on top of each other. Backup oxygen generators sit ready in case the primary system fails. Emergency chemical oxygen candles are stored throughout the boat, capable of releasing breathable oxygen through a controlled chemical reaction with no power required at all. Escape suits are designed to allow crew members to exit the submarine and reach the surface even from extreme depths, using pressurized escape trunks that didn't exist on older boats. Strict maintenance routines and constant emergency drills are now mandatory, because on a submarine, there's no room for human error when the stakes are the air everyone on board depends on. Every sensor, every valve, every filter has to function exactly as designed, every single day, without exception. The crew's survival rests entirely on a chain of components most of them will never see and rarely think about, until something goes wrong. Today's most advanced submarines have pushed this redundancy even further. Modern atmosphere control systems don't just monitor for CO2 and oxygen. They track dozens of different variables simultaneously, including humidity, trace contaminants released by paint, electronics, and cooking, and even subtle pressure changes that could indicate a developing problem somewhere in the hull. Some newer systems use predictive software that flags unusual trends in air quality before they become dangerous, giving engineers a chance to intervene long before any human on board would notice a difference. It's a quiet kind of engineering, invisible to the crew going about their daily routines, but it represents decades of hard lessons compressed into systems designed to make sure no one ever has to relive what happened aboard the Kursk. And here's the truth that changes the entire perspective. A nuclear submarine doesn't run out of air because it runs out of oxygen. It runs out of safe air the moment the system quietly cleaning that air stops working. The next time you picture a submarine gliding silently through the deep ocean, remember it isn't some massive air tank keeping the crew alive. It's a constantly running chemical machine, turning seawater into breathable life and scrubbing, second by second, the invisible threat hiding inside the air that 150 people, sealed between steel and crushing ocean pressure, depend on to survive. If you're interested in these kinds of deep dives into the hidden systems keeping people alive in the most extreme places on Earth, subscribe. What's coming next will be even more interesting.